Hello and welcome to GCSE Particle Model of Matter with Mrs. Castanera. We're on lesson 6, Changes of State. So our keywords for today's lesson are boiling, melting, freezing, condensing, evaporation and sublimation. And we'll know what all those words mean by the end of the lesson. So as you can see, we've got our exam board specification here. And that just tells us what we're going to be learning this lesson. Now I'd like you to start by answering the knowledge check questions, please. We're on page 31. Pause the video whilst you do that and then we'll mark them together. Okay, so let's go through those. Question 1, identify the 3 states of matter. That would be solid, liquid and gas. You'll need all 3 for the mark. Question 2, in which state are particles closest together? Well, that would be in a solid. Make sure you're marking in a pen of a different colour to the one that you wrote in to make it clear what's you correcting and what's you ticking to get right. Question 3, in which state do particles have the greatest kinetic energy? That would be gas. Question 4, identify the equation for density. So density is mass divided by volume, and I've put the units in there as well. You don't need the units to get it right, but that's absolutely fine if you have. An alternative way to write this equation out is to use the rho for density equals lowercase m times capital V, or just without the x if you prefer, either's fine. So that is also an acceptable way of getting the mark. Question 5, name the symbol for density. Well, it's rho written like a P, or sometimes almost like a sort of funny E/P shape, okay? So as long as it looks vaguely like one of these, that's fine. You don't need to write the name rho, you just need to have drawn the actual letter, the actual symbol. Identify the unit for density, so that's kilograms per meters cubed. Okay, make sure you've got that slash in there to show that it's per meters cubed. Question 7, rearrange the density equation to make m, which is mass, the subject. So mass equals density times volume, you can have that for the mark, or if you've written m equals rho times v, you can have that. So another way of writing that would be m equals rho v. Okay, either is fine. Okay, question 8, rearrange the density equation to make V the subject. So V is volume, so volume is mass divided by density. So that would be V equals M divided by rho. Okay, so give yourself a mark out of 8 there, please. So this lesson, we are going to be looking at changes of state. We're going to be able to describe the 6 changes of state. We are also going to understand why there is no change in mass when there is a change in state. Okay, so that's our aims, to understand these by the end of the lesson. So, vapours and fluids. The words fluids and vapour are used to describe a lot of everyday substances. We could describe many things as fluids. We talk about fluids as liquids, but sometimes we talk about fluids as gas. Vapour, we talk about water vapour, for instance. In science, they have specific meanings. So for science, a vapour is a gas given off by a liquid, even when the liquid is not boiling. Which is why we talk about water vapour evaporating from puddles and things. The puddles aren't full of boiling water, but the water vapour is evaporating off them. Also, a substance can be described as a fluid when each part of it, no matter how small, can change shape easily. So we often use the term fluids to describe liquids and gases. So both of those can be described as fluids. So moving on to page 32, we have an activity here about changing state, where you can observe the change of state of water from solid ice to a gas steam. And so normally this experiment is done by putting crushed ice inside a boiling tube or a beaker along with a thermometer and recording the temperature at regular intervals. So in this experiment it's every minute, and recording it over time and putting that beaker or boiling tube into hot boiling water. So we have a set of results for this. Well, you would normally record these yourself. You would record the temperature over the time every 10 seconds. Now, unfortunately, we can't do the practical. However, what I have done is I've provided you with the results, okay, which you are all going to copy out into your own booklet, please, and pause the video whilst you do that. So moving on to page 33, our next activity is plotting changes of state. And you'll begin to see now why I've given you the results, the data from that experiment, okay, because you're going to be plotting a graph. So using the results from the experiment that you've just written down, plot a line graph of time in seconds on the x-axis, which is along horizontally, versus temperature in degrees Celsius on the y-axis, which is the vertical axis. Now make sure you use a pencil and you add all the labels. Now, if you're happy and confident to do that activity and you know what you're doing and you're confident you can do that, you can plot all the results on the graph, then great, you can get started. Pause the video now and you'll need to potentially fast forward through me explaining how to draw the graph to get to the answers. If you're not confident, however, then we can go through that together, how to draw the scales for this graph. So the first thing I recommend doing is to use your pencil at the bottom of the page and draw a horizontal line along the edge of the page. So I've zoomed out just a little bit so you can see that more clearly. So very carefully take your pencil across the bottom of the page, drawing yourself a nice straight line. Now it isn't showing up very clearly on here, so I'm going to do this in pencil so you can see it better. So you can see there, I've drawn over it in pen so it's clearer for you to see because pencil was too faint for the video. I've just drawn myself two sets of axes here. This one across the bottom is going to be time in seconds, so we can label that. And this one, the vertical one, is going to be temperature in degrees Celsius, so we can label that too. So there we go, there's our graph with labels and axes so far. So we're already getting marks just by putting the labels on our axes. Okay, so it was a bit tricky working out the axes for this one, mostly because we only had 48 squares on the vertical axis and our temperature scale goes up to 100. So if we'd had 50 squares, we would have been able to say that each square was going to be worth 2 degrees Celsius, and that would have been quite easy. Unfortunately, we've had to make it a slightly shorter scale, so every 4 squares is going to be 10 degrees. So every square is worth 2.5 degrees Celsius. So let's label that on our graph. So we'll start out with 0, and then 4 squares later we've got 10, 4 more squares, 20, 30, and each one is 4 squares apart. Okay, so there we have our vertical scale for temperature, 0 to 100 degrees Celsius, and each of those is 4 squares apart for 10 degrees Celsius. Now the time horizontal axis. This time we had 80 squares across, and we need our time to go up to 330 seconds. So the easiest way to do that is every 10 degrees is going to be 2 squares. So it's 10, 20, 30, 40, 50. And so I've drawn little small lines to indicate each of the 10 degrees, and then a big line for the big numbers in 50s. Like so. So 50, 100, and so on and so forth. So then we have our horizontal scale from 0 to 350 this time. And as you can see, it's all nicely spread out and indicated there. So once you've got that done on your graph, then you can plot the points. If you're happy doing that, you can pause the video and then you'll have to fast forward to check your results against mine later on in the video. If you're not confident about that, then we can go through some of the point plotting together, which we'll do that now. So we have to have our results conveniently nearby. So put those next to you. Now our first result is at time 0, which is along this one, and temperature 0. So we put a little cross on our graph. Now it's quite hard to see on my graph in pencil, so I'm going to do mine in pen, and I'm going to do it in red pen so you can see it. But you need to do yours in pencil, okay, because you'll be able to see your work. The next one is 10 seconds, and it's also 0 degrees. In fact, it continues being 0 degrees all the way up to 40. There we are, they're all 0 degrees. Now, I'm going to pick a finer point pen because it's just a little bit chunky, that one, and my crosses aren't very distinct. So at 50 seconds, then the temperature goes up to 1. Now 1 is going to be somewhere between these two, not very far above the line. At 60 seconds, it's 2, which is just below the first line because each of these squares is worth 2.5. It is also 2 at 70 seconds. At 80 seconds, it is 4. At 90 seconds, it is 7. So 7.5 is 3 of these lines, so just below that one there. And at 100 degrees, it is 12. So we've got, if you're not sure about where to go, take your ruler. Okay, so 12.5 is the first full box square above 10. So it's just below that point there. And I'm doing crosses to show them clearly. So continue to plot these points, okay, and the same way I've just shown you, using, if necessary, a ruler, and you can use a pencil to go up and across if you need that to help you. That's absolutely fine. So pause the video whilst you do that, and then we can mark it together at the end. So let's go through that. Here we have all those points plotted on the graph. You'll notice quite quickly that we have one very clearly anomalous point. Perhaps the value was written down incorrectly, or the thermometer probe or sensor may have been completely wrong, or it could be in human error, they've read it incorrectly. There's lots of different ways of getting that incorrect reading. We will ignore that and not include it in our analysis or any further information in our graph. So you'll see there's a very nice curve. The water starts out at the same line, and then it curves up rapidly in an almost straight curve, but not quite, and then it plateaus off when it boils at 100. Okay, so you need to draw a curve of best fit for that. Okay, it can be a bit tricky. Feel free to use a ruler where it goes through the same temperature. Okay, I'm using a pen only so you can see what I'm doing. So you will need to use a pencil, please, for this. Same goes at the bottom. And then you need to, in one clean line, join up those points. So let's have a go at that. Okay, so you can see I've done that. There's a couple of areas where it's not perfect around here, where I'm missing a bit of data, it's a bit tricky. And again, it's not quite perfect at the beginning where it probably should have gone a bit higher. But I'm going to do it once and leave it because I can't rub those bits out because I haven't done it in pencil. You will be doing it in pencil, so yours will be perfect. Okay, so check that your graph has the same shape, that you've also identified your anomalous point. Feel free to label the anomalous point. Okay, so we've got ourselves an anomaly here. Okay, then we're going to have a look at part 3 on page 33. Okay, so we've got identifying changes of state here. So your graph, if all went well, should look a bit like the following. Well, in fact, we've only done part of this graph. So our graph starts off with our substance as a solid, and it melts, which is the first thing that's happening. Okay, and then it is a liquid, and then it boils, and that is the part of the graph we have. Okay, that's what we have in our graph. Now, it turns out that the ice is already melting here. So we've got our solid, melting substance, liquid, boiling substance, and gas. Now we can't label the gas phase on ours because we haven't drawn that, because you can't record water above 100 degrees Celsius. But we will do that to our graph now. So pause the video and label your graph. Okay, so ideally your graph might look a little bit like this. So I put my solid right at the bottom corner because actually even when I was recording this data here, or even when we would have been recording this data, this ice is already melting, it's already at room temperature, it's already beginning to melt. Okay, so the liquid phase is this whole part at an angle here. So all of this, your water is in liquid phase. And then we have boiling. And you'll notice that when the solid is melting into liquid and when the liquid is boiling into a gas, they're at a constant temperature, okay, indicated by the horizontal line. They're no longer increasing in temperature. Okay, so if you've got that correct, good, tick that. If not, then please annotate the corrections on there, please. So moving on to page 34. When changing state from solid to liquid, the temperature does not rise. In fact, this is true for all changes of state. When you change state, the temperature does not rise. Hence, the flat part on the graph, so that's where we see it in the flat part. This is because all the thermal energy being given to the substance by the Bunsen burner is going into breaking the intermolecular bonds inside the solid. And that's what turns it into a liquid. Now, once all the intermolecular bonds have been broken, the temperature starts to rise again. Okay, because then that thermal energy is available to be transferred to the kinetic energy of the particles. So the energy, first of all, is going into breaking the intermolecular bonds, and that's during the flat part of the graph. And there is no spare energy to heat the stuff anymore, right? But then once its bonds are broken, it's turned into a liquid, the temperature starts to rise again because all that energy from the Bunsen burner is transferring to the particles, giving them more kinetic energy, that's moving energy. And it's the same when changing state from liquid to gas. So all changes of state this applies to. So if we were to cool the substance, the graph would be the same but in reverse. Changing state from a gas to a liquid is called condensing, and from a liquid to a solid is freezing. So we know this. When condensing and freezing occurs, there is no change in temperature. When any change of state occurs, there is no change in temperature. When a gas is cooled, the kinetic energy of the particles decreases. Okay, so when you heat something or you cool something, you are changing the kinetic energy the particles have. Okay, so by cooling it, you're slowing the speed of those particles because the energy that they've got, the kinetic energy, has decreased. The particles move closer together. So when they have less kinetic energy, they vibrate less, they move around less quickly, and they move closer together. At the condensation point, which is when a gas turns into a liquid. Okay, we're going to underline this in a colour. And we're going to write a point over on the side here. So condensation point is when a gas turns into a liquid. You'll notice the condensation point, for example, if you're in the shower and if there's any glass or cold tiles or cold ceiling paint, for example, in your shower area, when the steam in the shower from the hot water has hit a cool surface like the mirror, the glass, whatever it is in your bathroom, you'll notice that you get condensation and water droplets form on those cold surfaces. So at this condensation point, which is when those water droplets are forming, intermolecular bonds begin to form, changing the gas into a liquid. So the thing that actually changes the state from gas to liquid is those intermolecular bonds forming. The same way that those intermolecular bonds breaking changes a liquid into a gas. Now, forming intermolecular bonds releases energy, and that energy maintains the temperature at a constant level. When all the intermolecular bonds have formed, then the temperature begins to fall again. Okay, and the reason for that is because the energy is no longer being released because they've all formed, and so the temperature begins to fall again because that energy is being lost to the surroundings, which are much cooler, and that cooler surroundings are absorbing the heat energy. Similarly, When a liquid becomes a solid, the temperature remains constant. So, what I'd like you to do now is have a go at the checkpoint question, please. Pause the video whilst you answer that. Okay, let's go through that. So, what happens to the temperature of a substance when it changes state, for example, when it melts or condenses? So, the temperature does not rise as all the energy is being used to break the intermolecular bonds between the particles or make. Okay, so that's our answer there. There are 2 marks for that. Give yourself a mark at 2. Okay, so the first part is saying the temperature doesn't change, or doesn't rise, doesn't fall, doesn't change. That's because all the energy is being used to break the intermolecular bonds, or they're being made and releasing energy. Okay, so we're going to move on to sublimation. Sublimation. So, sublimation, there are a few substances that turn straight from a solid to a gas with no liquid phase. This is called sublimation. So sublimation is turning from a solid to a gas without passing through the liquid phase. Going from a gas to a solid is called deposition. Now there's a video here on YouTube. It's very short, it's like a minute or so long. Okay, I want you to go to this link. You can click on it if you've got a digital copy of this booklet, or you can type it in. And I want you to then watch the video and then answer the questions below. Now you can answer these questions whilst watching the video if that helps. You may need to watch it more than once to be able to get all the answers. But as I said, it's a short video. So pause this whilst you do that. So let's go through our answers to those questions. Question 1, where did iodine get its name? Well, from the Greek word meaning purple. Question 2, what happened when an ice flask was used to cool the iodine vapour? Well, it turned from gas to solid crystals without becoming a liquid in between. And this process is called deposition. That's 3 marks. Give yourself a mark out of 3 for that, please. So, moving on to page 35, if you could answer the checkpoint question, what is sublimation? Pause the video whilst you do that. So, sublimation is when a substance changes from solid to gas without passing through the liquid phase. So there's 2 marks here, saying it goes from solid to gas and saying it does not pass through the liquid phase, or without turning into a liquid in between. So give yourself a mark out of 2, please. Evaporating and boiling. A liquid can change state without boiling. Even on a cool day, a rain puddle can dry up. We say the water has evaporated. Evaporation can happen at any temperature in the liquid state. So as long as it's a liquid, evaporation can happen at any temperature. Evaporation happens when more energetic particles leave the surface of the liquid, leaving behind the slower, cooler molecules. Now this is because not all of the particles in a liquid have exactly the same amount of energy. Some have enough energy to leave the surface of the liquid to break free and become gas particles, and that is the part of the liquid that vaporizes. It evaporates, okay, and that evaporation can occur at any temperature. Now boiling, or the boiling point, is the temperature at which vaporization occurs for the entire liquid, not just on the surface. So evaporation is about surface molecules on a liquid turning into gas. Vaporization is the entire boiling point is when the entire liquid vaporizes or turns into gas. So checkpoint question, what is evaporation? Pause the video whilst you answer that question, please. So what is evaporation? Well, it's when a substance changes from liquid to gas without boiling. Okay, so 2 marks here, from liquid to gas and without boiling. So give yourself a mark out of 2 there, please. So throughout all of these changes of state, the number of particles does not change, just their spacing and arrangement. So as a result, the total mass does not change. So you've still got the same number of particles, they're just arranged differently, okay, and less or more spaced out. We call these changes in state physical changes. So a change in state is a physical change. And that's because the process can be reversed easily. Okay, for example, by cooling it down instead of heating it up. This is very different to chemical changes seen in a chemical reaction. Okay, so the changes seen in a chemical reaction are very difficult to reverse usually, sometimes impossible to reverse. So for example, if you baked a cake, you would have egg, flour, sugar, maybe a little bit of milk, and you get a cake. Wonderful, very delicious. But reversing the making of the cake, could you ever get back the flour, the eggs, the butter, the sugar, bit of milk? Probably not. I don't think you could. So, checkpoint question, how does a change of state differ from a chemical change? So pause the video whilst you answer this checkpoint question, please. So let's go through that. How does a change of state differ from a chemical change? Well, a change of state can be easily reversed, unlike a chemical change, which is much harder to reverse or sometimes impossible. So again, it's 2 marks here, one for explaining that a change of state can be easily reversed, and the other for saying that chemical changes are very hard to reverse. So we're going to move on to the knowledge and application check on page 35. It goes on to page 36 as well. So pause the video whilst you complete those questions, please. So let's go through those questions. Question 1, describe the arrangement of particles in a solid. So they're in fixed positions, they're in rows and columns, they vibrate on the spot, you might have said, and they're a fixed shape. Okay, so for each of these you can have a mark up to a maximum of 3, so there are 3 marks available for this question. So a maximum of 3 marks there, even though there's 4 things you can say. Question 2, identify the state change from solid to liquid. Well, that would be melting. Question 3, identify the state change from liquid to gas. Well, that would be boiling. Question 4, identify the state change from gas to liquid. That would be condensing. And question 5, identify the state change from solid to gas. That would be sublimation. Question 6, describe the temperature during a state change. So temperature remains the same during a state change. Question 7, does the mass change during a state change? Well, the answer is no. Okay, you can have the mark just for saying no. The explanation, which I would like you to add if you haven't already got it, and feel free to use your notes page if you don't have enough room. So the reason is because the same amount of particles still exist, although you may not be able to weigh them as easily if the gas escapes. Okay. Question 8. What energy store do particles have? Okay, so they have kinetic energy. Question 9. Is a change of state a physical or a chemical reaction? Explain your answer. So it's a physical reaction for the first mark, and the reason is it can be easily reversed for the second mark, unlike chemical reactions. So give yourself a mark out of 2 for this question. Question 10. Explain what happens to particles as they change state from a solid to a liquid. Well, first of all, the kinetic energy of the particles increases. Okay, so we have increasing kinetic energy. Then intermolecular bonds are broken. And then finally, the particles can move further apart. So there are 3 marks for this question. Question 11. Explain why there is no change in temperature during the change in state. And that is because all the energy is being used to break the intermolecular bonds between the particles instead of increasing the temperature. So the energy is being used to break the intermolecular bonds, okay? There's no leftover energy to increase the temperature. Question 12, identify the unit of power, that's watts or the watt. 13, name the two things the energy of an appliance depends upon. Well, it depends upon the power of the appliance and the time, as in how long it's on for. So power is how much energy it draws from the system, from the grid, and time is how long it's on for. So 2 marks for that one. So give yourself a mark out of 19 for that, please. If you have 16 or more, then you've done very, very well. If you have 10 or less, then you need to be careful because that's quite a few errors you've made or a few misunderstandings there. So if you've got 10 or less, you really need to have another look at some of those questions, especially the first 8 questions, okay, because those are the more straightforward ones. Okay, if you've made a lot of mistakes from 9 to 13, that's more of a revision of previous topics and a very detailed understanding. Okay, so it kind of depends on where you've missed the questions as to what you need to do about that. But I recommend reviewing the lesson if you've got 10 or less. So before we finish, there's a couple of things to go through. First of all, we've got the keywords. Okay, so you do need to know what each of these keywords means and give a definition of it. It doesn't have to be word for word, but it has to be very close, using a lot of the keywords, such as the phrase vaporization, and the technical terms such as boiling, and things like that. So, and one further thing to do before the end of our lesson is that there is a video, a summary on YouTube. Here is the address, it's quite long, so if you don't want to be typing all that in, then I highly recommend that you get the digital copy of this booklet and click on the link and watch the video summary. And that's everything for our lesson today. If you have any questions, please feel free to email your teacher. Thank you very much.